Today we're going to see new method for you. It's called the root locus method. First we have to learn what the root locus concept is. So as you see on the screen, we have a very basic control loop where you have the reference point over here, and you have the error signal here. This is your system, and this is the output. So the one output of the system is feedback. This is our feedback loop, and that is compared to the reference point. And if you discover it, you have an error, then you go again. Look, okay, this is the way. But one thing that we don't have here is this is your system, you know. But we don't have it here is, why don't we put just a little bit of a control system, just a tiny block that would do something to this main system, would do something to this. So what we're going to do is, I am going to add in here just this simple block, a small block, and I'm just going to put it over here. You see, and we need just one simple proportional control signal, like here. Let's see if I can actually reduce the size to the point that makes it useful. Sometimes when you draw with these tools, you have to go with what the computer gives you, but there you go. I am making it in red ink precisely to make it different from the rest of the system, because this is our main focus today. Alright, what will happen if to my basic system loop I add this little block in here, and I add this little block in here with some value, some constant value in this case. So let's just put the thing, we're gonna put it here to make the contrast. We're gonna call it K. Okay, so let's just put some names. So this is your system, okay? This is your, I think I'm going to call it, let's call it control, and because it's a constant, we're going to call it control gain. Yeah, this one obviously is the output, and this is your feedback. This in here we already see this is the error, and that's the error that we are trying to correct. This is your reference. Again, just to make sure we are on the same page, if you have this just appear here, if you have this system that you, let's say you want to control the temperature of this room, so let's identify the parts. Let's identify the parts. This is the room. Yeah, the room, you measure a temperature, and temperature gets transformed into some sort of a voltage signal. That's what this feedback does. And the setting temperature also is like a reference voltage that you have set up. Let's say you want the temperature to be 80 degrees. So if the measured signal from here is not 80 degrees, let's say 75, the error is 5. So you introduce this block. Here's your control system, so that it will correct the temperature. Like this would be the equivalent of turning the heater on, and then how much of that heater, that's what this K is. And then you compare it again until you keep doing this many times until the error reduces to the minimum that you can. In some cases you may not be able to reduce it completely. In other cases you will, depending on what you're doing. So this is the basic setup. Okay, so now let me tell you a little story. Back in the 40s or so, Professor Evans at the University of Pennsylvania came up with this idea that if you actually have this system like this, if you have a system like this, where you have the this gain in here, with this setup that we have, he said that by changing K from 0 to infinity and plotting the results of the where the roots of the characteristic equation of the system went, he could predict whether he could control the system or whether the system would be unstable. This was his premise. Obviously, when you come up with such a brand new concept, and there might be some people that do not believe you, and in fact that's what happened to him. For about 15 years the IEEE would not publish his paper, and nowadays every control system book, including yours, has this method in it. Because what he said is, he says that if you have this loop, you can have the equations like this. Let me just say that you could say that the error is equal to the reference minus the output multiplied by the feedback. Do you see? That's how we figured out this error over here. Right? Is this signal minus this signal? That's what it's saying. So, and then you say that the output in here is equal to the K times G of S times the error, right? See? Error times K times G of S is the output, and the error is this difference. With these basic two equations you can do very wonderful things. Let me show you. Let's replace this into here. Yeah? And what do we have? The output is equal to K times G of S multiplied by R of S minus output of S times H of S. Yeah? Let's keep expanding this and and try to find a transfer function between the output and the input. So what we want, you say we want, so that you know where we're going, we want some sort of a relationship between these two. Yeah, this is what we want. So let's keep with the what we have up there. So you say the output of S is equal to K times G of S times R of S, yeah, minus K times G of S times the output of S times H of S, right? And then you identify that this term and this term contain the same signal, right? So move this one to the other side, and you're gonna have that the output of S multiplied by 1 plus K times G of S times H of S is equal to K times G of S times R of S. See? Okay. So from here you can very easily conclude that the transfer function that we are looking for between the output of S and the input, which is over here, this is obviously equal to K times G of S multiplied by, no, divided by 1 plus K times G of S times H of S. So this one in here, how can we call this transfer function? I think we can give it a nice name, and I'm doing this because it's important for you to know the basics of this thing. So this would be the transfer function, and this would be the closed loop transfer function. This one is a special transfer function because in here on this on the setup that we have introduced a control system which is just a constant, just a gain. Okay, so what Professor Evans was saying is that he is saying that if you say K is 1, because if you say K is 0, then the whole thing doesn't work. If K is 1, you get the transfer function, right? And because you change this number here, if K is 2, the poles are different, and so possibly the zeros too. Remember those two names, just to make sure that we're on the same page. The zeros are the roots of the numerator, and the poles are the roots of the denominator. So the point here is that if you keep changing K from 0 to infinity, sooner or later you are going to end up doing some sort of a plot of where these roots are. So let me try first before I show you this presentation that I have, just trying it by hand, how that may look like. If this is my plane, the complex plane, I may say, okay, wait, when I do when k is equal to 1, let's say you may have roots over here. When k is 2, they might come here. See, they get closer like this until you begin having roots like this as you keep changing. See? Or maybe they begin going like this. Remember, k is changing all the time. And then maybe goes like that. This is a situation where every time that I have a value of k, I have one of these numbers. So the path, the plot that of those, let me put the green color. If I were to do a line over here and one like this of all that lossy, like this, I need to make it through this one, right? If I join all those points, if I trace them rather, this thing is called the root locus. Because it is a plot of where the roots of the system are depending on the value of k. Now, you know that if you have roots, I think by now you know that if you have roots like this, you could predict what the output is, right? In fact, I am going to put it in red color here. Let's try this. Of course, there's always coming conjugate pairs, right? But we know for sure that the output of this is going to be something like this. And the output of this one is going to be something like that. But remember what the output of this one looks like? This one will go boom, 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 boom. And it would be totally unstable and it would blow up the system. So you begin to see why what Evans was saying was so important. Because he could actually, by doing this, by changing the value of k, he could actually predict where this point is. You know, that's the point where the root crosses the axis, and that is the point where you could say the system has a limit. You cannot put more control in there unless you want to create a major problem. And we are not here to create problems, we're here to solve problems. So that's the basic concept. So having done this, I'm going to show you some slides that talk about the different kinds of plots or locus that we can get of systems. Now, I can tell you ahead of time that by using our bond graph technology, once we have a transfer function, we can test that transfer function by using this method and changing the value of k and getting the plot. So that's where we're going. So we'll do that. But first of all, let's just look at some slides that I have expanding the concept of this, what I've just told you. So here we have the basic control loop. As I mentioned to you, this is the reference point, this is the output. And to make it even simpler, we are going to do a unity feedback. So h in this case is 1, right? So h is 1. So in the expression that we had a moment ago, let's just take go back for a second, and if we have in here, what happens if if h is equal to 1? Can we modify this in here? We can, if h is equal to 1, we will have that the output of s over the input in here, this would be g of s divided by 1 times k times g of s. This would be the transfer function that we have on the system that I just showed you on this one. See? So we are going to be experimenting and seeing what happens when we change k from 1 to infinity. So if you put something like this together, and you have this kind of if you have this kind of transfer function in here, you know that one of these is at 0 right here, and the other one is at -a when k is equal to 1. And if you keep changing, you are going to have this root locus here. So if you have this the plot of all the roots, this is what we'll have. So you will have one at -a like this, and then you'll have one over here. So do you see what I'm trying to say? What is the denominator of this over here? Is s squared plus a equals to 0, right? So what are the values of s? S is going to be plus or minus the square root of a, right? These values here are those guys, that point and this one. And so if k is equal to 1, then you have a different thing, because you will have to go back to the expression that we did. K is equal to 1, then we have this. So we want to keep plotting the roots like that, and in this case that's what they do. See these arrows as they go, and then they go this way and that way, like this. Okay, so for this particular system that you have on the screen, the system will never go unstable. Yeah, so it is a matter of us getting the correct transfer function in MATLAB and seeing what this does. And I'm thinking that I am the proponent of seeing things in the practical way, not just the theoretical way, because right now I am to the point where if this is true, if what I said is true, we should just put this transfer function in MATLAB and ask for the root locus, right? And I think we should do that. I think we should just go over here to my my system here, and I am going to enter that transfer function into MATLAB, and let's go over here and just have that transfer function on the screen and running. MATLAB takes a little time to wake up on the system that we have, but let me just go back to what I was saying. Where's the we need to go back to the transfer function that we want, to this one. So let's say that a is 5. So the transfer function that we have is 1 divided by s times s plus 5. Yeah, this is my transfer function. Let's call it g. So I am going to enter this transfer function into MATLAB, and then I'm going to ask for the root locus, and it should come up with something like the one on the right hand side. How in the world do we do this? Okay, we're still waiting for MATLAB to give us a prompt, and hopefully it does that pretty soon. Okay, let me see if we got the MATLAB prompt already or not. Or still thinking about it. There we go. It came, but okay. One thing that I believe is that you could enter it in polynomial form, or you could enter it as an algebraic expression. Let's try the polynomial form for today. So this one, what did we say was 1, right? So if you put this just as a 1, this is just the numerator of this. No. Let's see, what are we doing here? We need to put the correct parentheses like that, and then the denominator. The denominator is going to be s squared plus 5, right? So s squared would be 1 for s squared, plus 0 for s, and then 5 for the constant term. So there it is. So I am going to create the transfer function g is equal to the transfer function of the numerator and the denominator. Yeah, there we go. So right now I have exactly what I wanted in terms of the transfer function. And I told you that, so I'm going to say R locus, please give me the root locus plot of the transfer function g. The computer goes and thinks about it for a moment, does all the calculations, and pretty soon we should have an answer. Right? Our minds are faster than the computer, see? So I'm just waiting so that we can, there we go. You see? Here's where we have this this plot in this case. So if we have a different kind of transfer functions, we'll have different plots. So you see here you have this transfer function, and if we have something like this, see, now you see in here the situation is different, because if we enter this transfer function of the denominator and we enter this one over here, this is what we will have as in terms of the plots. Now what you're seeing in the slide, you have a couple of words that you that we haven't mentioned. This is asymptotes and breakaway point. This technique, and of course your textbook also talks about it, but I wouldn't pay too much attention to it because with MATLAB we can get the plots directly. This is if you want to plot it by hand, you want to be seeing where where the plots are, or where the breakaway points are. In other words, you want to be able to predict that graph. With MATLAB we don't have to predict anything. We have the graph. So something to understand, just a matter of procedure, you may say. When you have a location of one of the roots in here, you could try to analyze how the angle is to the to that place, and you say the parting vector. This again is for plotting by hand, and I would not pay too much attention to it. But here it gives us, if we have this kind of transfer function that has this format, we should be able to know, if you have this format, you will get something like this. See? So if you have if you don't have MATLAB, you may need to worry about this called angles of departure or the asymptotes. But I really am not going to make to do an emphasis on that, but rather, if you have MATLAB, this is what the root locus would look like. What I think is important is that you could let me see, pointer options. I want to change the color of the pen. Well, I may not be able to. Okay, the reason I wanted to do that is because I wanted you to see how the roots change. So if they start over here, they come this way, and then they move like that. See, in this case, this is a third order system, see? Because S is cubic on the denominator here. I think it might not be a bad idea if we try something like this. In fact, maybe we should do that. Sorry. Let's try this, huh? Let's see for a second. Let's propose a transfer function ourselves. Let's just say that this is 1, and then I am going to say this is S, and let's just put this a 2. How is that? 2S plus 1, and then I'm going to put like a 5, S plus 1. How is that? So I'm going to teach you how to enter this kind of transfer function and obtain the root locus plot. So let's just go to our MATLAB. Remember the transfer function, because I don't know if we'll be able to see it again. So let's see. I want to go over here, right? What was the we're going to do something a little different here. We're going to say that S is, well, first of all, let's clear all variables here. So let's clear all variables, and then we're going to say S is equal to the transfer function of S. Here is going to be like, I think we need this one. Let me see if this is correct. And it is correct. What I just did is I said, make the variable S transfer function type. That's what I just did. So I am going to say that my transfer function G is going to be equal to 1. I'm just going to give it like a parentheses, perhaps, like that. And then I'm going to say, just like I'm writing an expression, S, what was the, and then we have to do the parentheses here for the denominator, right? S multiplied by, what was the 2, right? 2, computer understands like this, plus 1, right? And what else did I have? I had the 5, right? 5, and then multiply by S, and then plus 1 was there also? Am I right? This was the transfer function that we had, right? And then I think I need to close the parentheses. And lo and behold, I have my transfer function here. And now I can say R locus of my function G. Of course, MATLAB has got this plot for me. Okay, let me see. There we go. You see what I mean? So any transfer function that we have, you can actually do this. Now MATLAB has some very nice things, because you could actually click on a location here. Do you see what it does? It gives you the value of the gain, what the roots are, what the damping is, what the overshoot is, and at what frequency. See, any place on the root locus that you click, it will tell you that. See, gain 14. I don't remember what was the other value. Here is gain 0.07, and it will tell you even where the unstable region is. See, with this kind of gain, you have problems. But you can study the system by using this root locus. So the root locus plot is a very useful thing. So I'm going to stop this video here, which the objective of which was to show you how to get the root locus plot. When I was in school, we did this by hand, and using those asymptotes and angles of departure and all the stuff that in your book you will find. But I'm not going to lead you that way. I'm leading you this other way. Just find a way to enter your transfer function in MATLAB, and you'll get your root locus plot for what you want to do. Now, how in the world this is important for design? The thing is, with certain value of k, you already know that your system is stable or unstable, but not only that, you know by clicking in here what the damping is, what the overshoot is. Remember, the overshoot is the amount over the settling point that we want, and we could impose on that different restrictions so that we could actually see where we are on our design, or design it for a particular overshoot or things like that. The point is that this is the tool for designing controls. So I have shown you now only what we know the transfer function. But one thing that you would notice is that I said nothing about the system. Question is, where did that transfer function came from? I just gave you assuming that we had a system and we found a transfer function, right? But that's not exactly with the way we have done things in this class. We started with the system itself, right? And then we found the transfer function, and then we did this. So then the next video that I want to do is I am going to start like that, with the system, obtain the transfer function, and then end up over here. So now, granted that your textbook is concentrating more on the graph, on what the root locus is, and but we have this wonderful bond graph technology that in just a few seconds we could obtain the transfer function by describing the system to the computer. See, so if you study just a particular system and you're given the transfer function, then we do what is in chapter 8. But if we don't have the transfer function, then we need to go back and use the skills that we have learned from the beginning of the semester. Okay, so let's stop this now. I think we achieved the objective of showing you how to obtain the transfer function, how to get the root locus plot from the transfer function.